In the last video, we took a look at two models of population growth. We described each model using a differential equation. So we had the natural growth model and the logistic model. This was the differential equation for the natural growth model, and here is the logistic differential equation. We solved both of these differential equations, and we got the function for the population at any time t for both of these two models. So let's summarize what our findings were and work through a couple more examples. First of all, for the natural growth model, the differential equation is dp dt equals some constant k times p. For natural growth, the population grows at a rate proportional to the current size of the population. We found that the general solution for this differential equation is population at any time t equals the initial size of the population times e to the kt. K here is called the relative growth rate, and that's dependent on the type of population that we're studying. Then we solved the logistic growth model. The differential equation for logistic growth is dp dt equals kp times 1 minus p over m. And after a rather lengthy process, we found that the solution for the population function for logistic growth is population at any time t equals the carrying capacity m divided by carrying capacity minus initial population divided by initial population times e to the negative kt plus 1. Once again, k here is dependent on the population that we're studying. M is the carrying capacity for the logistic growth model, and this was what we found in the last video. Let's take a look now at example 3. We want to know at what size of population will the natural growth model experience the most rapid growth, and at what population level will the logistic growth model experience the most rapid growth rate. To solve example 3, we're really going to focus on the differential equations, and we want to know not at what time the growth rate is largest, but at what population level the growth rate is largest. So let's solve this. So again, the question is, at what population, so at what value of p, do we have the most rapid growth? First, let's look at the natural growth model. So the differential equation for the natural growth model, the rate at which population grows is k times p. Notice that as p gets larger and larger and larger, so does dp dt proportionally. So the larger the population, the faster the population grows, which gives us a larger population, which makes the population grow faster, which gives us a larger population. This is never going to end. So at what population do we have the most rapid growth rate for natural growth? Well, this is unbounded. The population continues to grow without bound if there's nothing to stop it. So we could say, I guess, at infinity population, we have the most rapid growth, but really the growth rate is unbounded. We keep getting more and more growth as the population gets larger and larger and larger. So the natural growth model might work well to describe a population in the short term, but in the long term, we really have some unrealistic behavior. How about the logistic growth model? When does that, or at what population rather, does that have the fastest growth? So for the logistic model, the differential equation is dp dt equals k times p times 1 minus p over m. I want to know what is the value for p that gives me the largest growth rate. I'm trying to maximize growth rate. And just for this problem, I think it's sort of helpful to think of the growth rate just as a function of p. So yes, it is dp dt, but just in terms of this problem, let's lose the dp dt notation, and let's just call this some function, and I'll call it r so that we think of a rate here. So I'm going to call this some function of p, r of p. And this is just for this problem. It's really not the best way of thinking of the notation, but I'm just trying to emphasize that the growth rate is a function of p. And if we want to know at what population we have the largest growth, we are trying to maximize this function with respect to p. This is actually a calculus 1 problem, trying to maximize a function. How do we find the maximum value of a function? Well, we would take the derivative, look for critical numbers, and see if the critical numbers give us a maximum or a minimum. So that's exactly what I'm going to do here. I'm going to take the derivative of this logistic differential equation with respect to p. Before I do that, I'm going to expand this out to make things a little bit simpler. So this rate function, as we're calling it here, is kp times 1 minus kp squared divided by m. I just expanded this out. Now to find critical numbers, I take a derivative. The derivative with respect to p now, so I'm taking derivatives with respect to population because I want to know at what population I have the fastest growth. Derivative with respect to p is k minus 2kp divided by m. I'm looking for critical numbers. So to find critical numbers, I set the derivative equal to 0. I'm trying to find the maximum of this function. To find the maximum of a function, we take the derivative. We set the derivative equal to 0 to find critical numbers. Now I'm going to solve for p. That will tell me at what population I have a critical number. So first thing I'm going to do here is to divide each side of the equation by k, or I'll just think of multiplying 1 over k on both sides. So on the left-hand side, these k's cancel out. And on the right, 0 times 1 over k is still just 0. So I get rid of the k, and I have 1 minus 2p over m equals 0. So 1 equals 2p over m, and I'm trying to solve for p. So I'm going to multiply by m on both sides and divide both sides by 2. So I've solved for p. The 2's cancel, the m's cancel, and I have p equals m over 2. This is a critical number of the rate function for the population. When we find critical numbers, we need to verify that the critical numbers actually give us a maximum or a minimum. So how do I know that I actually have a maximum at this critical number? Well, this equation is what I just optimized. And my variable here is p. So this is a quadratic equation in p, and we have a negative on the p squared. So if we were to graph this in terms of p, we would have a parabola opening downwards. The critical number gives us the point at which the parabola reaches a maximum, where the derivative is 0. So that's why this critical number does give me a maximum of the rate function here in terms of p. So when population equals m over 2, that's when I have the very fastest growth rate for the logistic model. So let's summarize this with a nice statement. So for the logistic model, population grows the fastest when the population has the current size of half of the carrying capacity. We will see this visually in the next couple of examples. But this says when the population is half of the carrying capacity, that is when the population has the fastest growth rate. Let's take a look at example 4. Here we have our rabbit population. And I guess we have a larger island now because now our island can support 30,000 rabbits. So we have a colony of rabbits living on an island, and they grow according to the logistic model. The island can support 30,000 rabbits. So this is the carrying capacity M. The initial size of the population is 100 rabbits. So this would be P sub 0. And after 1 month, the population is 150 rabbits. Using the solution for the logistic differential equation, we are going to write a function that describes the population of rabbits at t months. Then after we find that population function, we're going to figure out exactly how long it will take until the population reaches 20,000 individuals. Rather than working through this problem by hand, I want to show you how we can use Mathematica to simplify the busy work here. All right, I've got Mathematica up and running here. And first, we're going to just define the different parameters that we have for this problem. So I'm going to define the carrying capacity, that is 30,000. And then the initial population, I'm just going to call P0. This is 100. Now I'm going to write the solution for the logistic differential equation. I'll define this as a function. P of t equals m divided by m minus p0 divided by p0. This is times e raised to the negative kt power. And then we add 1. So here's the function that will tell us the population at any time t. Now we want to know the value for k. We don't have the function just in terms of time. We have some constants for m and p sub 0, but we need to solve for k. And we're going to do that by using the condition that we're given. We're told that after 1 month, there are 50 rabbits. So I'm going to define these, and then I want to solve. After 1 month, there are 50 rabbits. So population at time 1 equals 150. I need 2 equals here, and now I want to solve for k. So this is going to give me the k value, and then I'll use that to get the final expression for the population function. Now, if I just run this, I get something that's sort of confusing here because it's giving me some complex solutions. So I just want solutions over the real numbers. So in the solve here, I can just put comma reals. And this expression is a little bit long and messy, so I'm going to simplify. And this is the value for k. So now that I have the value for k, I'm going to plug that into the population function, and then I'll have the population function all in terms of t. So I'm just going to set k equal to this. And now the population function is this right here. Notice that it kind of simplified for me. I don't have the e to the power here because the e and the natural log canceled. So Mathematica did some automatic simplifying. But this is the population function. Let's see what the population function looks like in Desmos. There it is. This is describing the population of the rabbit colony at any time t. We have the number of individuals on the y-axis. On the x-axis, we have time measured in months. So after 5 months, we have about 750 individuals. After 10 months, we have almost 5,000 individuals. And look at this, after 2 years, 24 months, we have like over 25,000 rabbits. That's kind of rapid growth. This is only measured in months, and we started off with only 100 rabbits. This is quite an incredible growth process here. So there we have a population function for the colony of rabbits on the island. There's one more thing that we wanted to solve in the problem. We want to know at what time will the population reach 20,000 individuals. So 20,000 individuals, that's right there. We want to know what time value gives us 20,000. So it's going to be a little bit more than 15, maybe 15.75, somewhere around there. But let's find it exactly using Mathematica. In order to find when the population is 20,000, I'm going to solve for population of t equal to 20,000. Solve for t. Once again, I want a solution over the reals, and I'm going to do a numerical solve here, n solve, so that I just get a decimal answer. So 15.7. At 15.7 months, the population reaches 20,000 individuals. Again, this is starting at 100 rabbits. And this might seem a little bit drastic, like only a year after the population starts, we're already at what? A year is 12 months, so we're already at 9,200 rabbits. This seems a little bit drastic, but I think this is actually kind of a tame estimate, because if we started with 100 rabbits, the gestational period for rabbits is about a month. And if we only have 150 rabbits a month later, that means only 50 new rabbits have been added. But if we had 100 rabbits with 50 pairs, and the average size of a rabbit litter is 6, then we'd have 50 times, we'd have 300 plus the original 100. It's kind of more realistic to look at like 400 rabbits after the first month. So this is really rapid growth, but I think it's maybe not even as realistic as what it could be for how fast rabbits reproduce. So just for comparison's sake, let's actually see what it would look like if the population after 1 month were a more realistic number like 400 rabbits. And that sounds like a lot, going from 100 rabbits to 400 rabbits in 1 month. But again, if you've got 50 pairs of rabbits and each pair mates and has a litter of 6 rabbits, then, well, that's 50 times 6, 300, plus the original 100, that's 400 rabbits. So let's see what the population function would look like if we had 400 rabbits after 1 month. So here in Mathematica, I want to clear the value of k. And then I still have the same carrying capacity, the same initial population, but now the population at 1 month, I'm going to choose to be 400, just to see what happens. So I'll solve for k in this scenario. And here's the value for k. So I'm going to set k equal to this new value. And the population function is a little bit different. Let's take a look at this in Desmos. So if after 1 month we have 400 rabbits instead of 150, then population would look like this. Quite a lot more drastic population. We reach close to the carrying capacity way sooner. Before even a year, the population is basically at 30,000. So much more rapid growth if we have 400 rabbits after 1 month. Finally, for this section, let's look at example 5. We're told that a population, measured in thousands, develops according to the logistic growth model. And here's the logistic differential equation. So we have some specific numbers here. We want to know what is the initial relative growth rate, that's K. What's the carrying capacity? And then we're going to take a look at the slope field for this differential equation. So first of all, let's try to figure out what is K and what is M. When you look at this differential equation, it doesn't really look like it's in the form for the logistic growth model. We can rewrite this though, so that it will really match the sort of form that we're used to. So we're going to rewrite this, and that will give us the value for K and for M. Then we'll proceed with the rest of the problem. So for this problem, our derivative is 0.3p minus 0.02p squared. What I want to have out front is a multiple of p. So I want to have something times p times 1 minus something. And in order to get there, I'm going to factor out a 0.3p from both of these terms. So I factor out a 0.3p, and the first term I have is 1, and then I'm going to factor it out of here. That just means I'm going to divide this term by 0.3p. So I can write minus 0.02p squared divided by 0.3p. This might look a little bit confusing, but imagine going the other direction. Imagine distributing through to both these terms. We'd have 0.3p times 1, and then 0.3p times this fraction. The 0.3's would cancel, and we would be left just with the numerator. So we can factor just like this. Now we're getting closer to the sort of form that we want. We have something times p times 1 minus something, and we still want to write this expression as p over m. Well, we can cancel a p in the numerator and denominator. So I have 0.02p divided by 0.3, but I want to have just p divided by m. So I need to move this constant of 0.02 downstairs. I can do that if I divide in the denominator by 0.02. So I can move something from the numerator to be in the denominator of the denominator. So this looks like this. We have the 0.3p times 1 minus p divided by 0.3 divided by 0.02. Now this is the value for m, and this value for m turns out to be equal to 15. We can throw that in a calculator, 0.3 divided by 0.02, and that equals 15. So now we can write the logistic differential equation in the form that looks more familiar. 0.3p times 1 minus p divided by 15. This is dp dt. So we've just rewritten the differential equation that we were originally given. So now it will match the standard form for the logistic growth model. Part A, what is the initial relative growth rate of K? That's the 0.3 here. So the value for K is simply 0.3. What is the carrying capacity? I find the carrying capacity in the denominator here. The carrying capacity is 15. This tells me that the population I'm thinking about here can reasonably support up to 15,000 individuals, since we're measuring in thousands. For part C, we have the direction field for this differential equation. And looking at the direction field here, I think will really help to understand more about the logistic growth model. We have population measured on the y-axis, and on the x-axis, we have time measured in months or years or whatever we're measuring time in. And what we want to do is graph specific solutions for the population function using different values for the initial population. So these are values for p sub 0. These would be starting values along the y-axis. We want to look at what the different particular solutions for the logistic growth model look like in this case. So let's start with an initial population of 1. And since it's measured in thousands, this is actually 1,000. So right here, this is where we have an initial population of 1,000. And we just want to follow the lines of the slope field to graph the particular solution. So it starts off with a fairly slow curve. And it ends up looking something like this. So if the population starts off with 1,000 individuals, that's what the solution function looks like. How about if the population starts with 5,000? Well, that starts right here. So let's graph that particular solution. Looks something like that. Now we can do 13. 13 is right here. And 13 will look something like this. A very slow growth. Notice how this is almost horizontal. So if the population is already 13, really close to the carrying capacity, we'll still have some population growth, but it's going to be very, very gradual because we've almost reached the carrying capacity already. What if we start with a population of 15? Well, if we start with a population of 15, then we're already at the carrying capacity. That's right here. And since that's the carrying capacity, we have the equilibrium solution. The population just stays completely static. It neither grows nor declines. So we have a perfectly horizontal line here. Let's look at the last scenario. What if the population starts at 20,000? Somehow we've got more than what the environment can handle. The carrying capacity is only 15. So what if we start at 20,000? Here's what that graph looks like. We start at 20,000 and we have negative slopes. The population is declining until it starts getting closer and closer to 15. Think back to something that we learned in problem 3. We wanted to know at what population size we'd have the most rapid population growth for the logistic model. And we found that we have the most rapid growth at half of the carrying capacity. So most rapid growth, that's when the population equals the carrying capacity divided by 2. For this particular example, the carrying capacity is 15. So we'd have 15 divided by 2, which is 7.5. So if we have a population of 7.5, we will have the most rapid growth. 7.5 is right here. And look at the slopes of the slope field lines. The slopes are steepest right around 7.5. That's exactly what we expect from the work that we did to figure out at what population we have the most rapid growth. So we have the very steepest slopes when population equals 7.5, just as we expect. And we can see that very clearly in the slope field. Finally, let's write a function that describes the population at any time t. So we're just going to use the general solution that we found from the logistic growth model, and we're going to use the value k equals 0.3 and m equals 15. So that function, the solution for the logistic growth model, is m, which is 15, divided by m minus p sub 0, divided by p sub 0, times e to the negative k, and k here is 0.3, so negative kt plus 1. So we could take different values for the initial population, plug them into this function, and this function describes the population at any time. Let's actually plot this in Desmos. We'll take the same initial population values that we had when we drew them into the slope field, and we'll see how the actual curves in Desmos compare to the curves that we drew by hand in the slope field. Our population function is p of t equals 15 divided by 15 minus p sub 0 over p sub 0 times e raised to the negative kt. K was 0.3, so negative 0.3t. All of this plus 1. Now let's add values for the initial population p sub 0. And we'll start with p sub 0 equals 1. There we have it. That is the curve that we drew. That looks pretty close to what we drew by hand. And then an initial population of 5. There's that one. Initial population of 13. Initial population of 15. That's, once again, an equilibrium solution. It's just a flat horizontal line. And finally, initial population of 20. There we have population decline because we start above the carrying capacity. We can actually plot all these at once and see them all together. So we'll do 1, 5, 13, 15, 20. And there we can see all the different population curves that we just drew by hand. Now that we've seen differential equations apply to a variety of real-life situations, I hope that you have an appreciation for how powerful differential equations are and how useful they are for modeling real-world phenomena. So first thing I'm going to do is divide each side of this equation by 0. Yeah, that's a great idea.